Hello, this will be a demonstration of Proposition 24 from Book 6 of Euclid's Elements, which says that in a parallelogram, the parallelograms about the diameter are similar both to the whole and to one another. What this is going to look like is we're going to have the parallelogram A, B, C, D, this, A, B, C, D, and we're going to have its diameter AC like so. And about this diameter, we're going to have two parallelograms like this. This is going to be the parallelogram AEFG, and how exactly is it? FHCK, like so. So AB is going to be parallel to DC and parallel to GH. Likewise, AD shall be parallel to BC and to EK. And what we're going to prove is that these two parallelograms, EG and HK, are similar to both the whole parallelogram AC and to one another. We're going to focus on the two parallelograms EG and AC for right now. We're going to prove that those two parallelograms are similar to each other. Now, EF being parallel to BC, so EF being parallel to BC, within the triangle ABC, we have some straight line EF, which is parallel to the base BC, which means it cuts the remaining sides proportionally. That's proposition 6-2. So BE is to EA, just as CF is to FA. And similarly, because FG is parallel to CD, again by 6-2, CF is to FA, just as DG is to GA. Now we have two ratios, BE to EA and DG to GA, which are the same with the same ratio, namely CF to FA, which means by proposition 511 they are the same with one another, so that BE is to EA, just as DG is to GA. Now, BE being to EA, just as DG is to GA, we have just shown this to be the case. By proposition 5A componendo, BA, which is the sum of BE and EA, is to AE, just as DA, which is the sum of DG and GA, is to AG, so that BA is to AE, just as DA is to AG. And we can alternate this proportion by proposition 516 to say that BA is to AD, just as EA is to AG. Now, GF being similar to DG, we can say by proposition 129 that the angle AFG is equal to the angle ACD, because these are corresponding angles, which means by proposition 129 they are equal to each other. And with the two triangles AFG and ACD, they have one angle equal to one angle, a second angle which is common to both, so a second angle that is equal to a second angle, which means by proposition 132 and some other stuff, that the third angle AGF is equal to the third angle ADC, which means that the two triangles AFG and ACD are equiangular. And so, being equiangular, the two triangles ADC and AGF being equiangular, by proposition 6-4, the angle-angle similarity theorem, AD is to DC, just as AG is to GF, and DC is to CA, just as GF is to FA. And we can prove in a similar manner that the triangle ACB is equiangular with the triangle AFE. That would look something like, give me one moment just to see everything. There we go, okay. So this would go something like this, EF being parallel to BC, the alternate angles AEF is equal to the to its corresponding angle. I think I said alternate, they're corresponding angles. The angle AEF is equal to the angle ABC, and the angle BAC is common to both the triangles AEF and BAC, which means between the two triangles BAC and EAF, we have two angles which are equal to two angles, which means that the third angle AFE is equal to the third angle ACB, which means that the two triangles AFE and ACB are equiangular with one another, which means by proposition 6.4, they are similar. The sides about the equal angles are going to be proportional, so that AC is to CB just as AF is to FE, and CB is to BA just as FE is to EA. Now, having shown in step 6 that DC is to CA just as GF is to FA, and having shown in step 7 that AC is to CB just as AF is to FE, by proposition 5.22 XI quali, we can say that DC is to CB just as GF is to FE. So going through this equal term CA and going through this equal term, excuse me, give me one moment, AF, we can compare the extreme magnitudes directly to say that DC is to CB just as GF is to FE. Again, that's proposition 5.22. Which means that the two parallelograms EG and AC have been shown to be equiangular to each other. Okay, they haven't exactly been shown to be equiangular with one another, but you can add up the two triangles that make them up. So, like, for example, the angle at G is equal to the angle at D, and the angle at E is equal to the angle at B. And the two triangles which make them up are equiangular, which means that adding them together by common notion 2 will produce more equal angles. So, for example, the angle at A here is common to both the parallelograms EG and AC, and with parallelograms, the opposite angles are equal to each other. That's proposition 134, I'm pretty sure. So the angle EFG is going to be equal to the angle BCD. So altogether, the parallelograms EG and AC shall be equiangular, and they've just been shown to have the sides about the equal angles proportional, which means by the first definition of book 6, they are similar to each other. That is the definition of similar rectilineal figures, that they are equiangular and that they have the sides about the equal angles proportional, which means that the parallelogram AC is similar to the parallelogram EG. Now, we can go through this whole process again to show that the parallelogram AC is also similar to the parallelogram FH, which means we have two rectilineal figures, parallelogram EG and parallelogram FH, which are similar to the same rectilineal figure, parallelogram AC, which means by proposition 6.21, they are similar to one another, so that the parallelogram EG is similar to the parallelogram FH. And this is all that we set out to prove. We set out to prove that the two parallelograms EG and HK are similar to the whole parallelogram AC, and that they are similar to one another, and we have just shown all of this to be the case, which means we are done with the proposition, therefore, etc., QED. I've got nothing to say about this proposition, so I'll end the video here and move on to 6.25.